Hello everyone, welcome to today's Crunch seminar. This is our first seminar in 2024, so Happy New Year to all. Today we have two talks by two speakers. Our first speaker is Zhiping Mao. He will be giving a talk on neural operator learning enhanced physics informed neural networks for solving differential equations with sharp solutions. Professor Mao obtained his bachelor's degree in 2009 from Changchun University and PhD degree in 2015 from Xiamen University. He then joined in the division of applied mathematics, Brown University, as a postdoc. He mainly interested in numerical solutions of PDEs and deep learning, and he published more than 30 science papers on top journals, including 7 highly cited papers. With that, we invite Professor Mao to begin his presentation.
Okay, thank you. Thank you for the introduction, and thank you, George. So yeah, I'm a little bit excited because this is my first time to give a talk back to Crunch Seminar after I left Brown. So yes, it's more than 3 years. So it's a great honor. So thank you. So uh, today I'm going to talk about one of my recent work, which I think the second one is Zhiping Mao, and I think most of you know him, Zhiping Mao from Dalian Technology, and George and Bin is my first master student, and he is now looking for a PhD position. So yeah, the most of the coding is done by my student Binin. So yeah, so my talk the topic about my talk is about by combining the operator learning and the ping like deep ONet or and the ping. So I think most of you are very familiar with this the previous two things, and the equation I solved is like kind of uh, the PDEs categorized by sharp solutions like Burke's equation, like some kind of Navier-Stokes equation with high linear RE number. So this is the outline of my talk. So yeah, first I will briefly introduce these two ping and the DeepNet, and I know all of you are very familiar with this one. So I would not take too much time on this. Then I will introduce what's the idea, a basic idea, and how we do for our new algorithms. And then I will give some numerical examples followed by a short summary. So, so I will skip this one, and this is the framework of deep learning. Usually, when I give a talk in China, I will introduce this one. So I just briefly introduce one. Like neural network-based machine learning is nothing but neural network is a function, and you use this kind of function to approximate the solution of PDE or something others. And once you have this function, and you have this surrogate function, and you can use this kind of surrogate function to formulate a loss function, and then you have a loss function, and then you can using some kind of the optimizer to train your neural networks, and this is the basic framework. So I think all of you very familiar with this one. So I was just give us just skip this one, and I will take a little bit of time to explain this picture. So this picture is about the errors in deep learning. I think this is about the analysis. Like for the error in approximate function or approximate solution of the PDE, like most of you know, there's 3 kind of errors. The first one is the approximate error, and the second one is the generalization error, and the third one is optimization error. What is the optimal error? Is like once you set up your neural networks, then the approximation error is fixed. Like this is the this is the distance between your target function and the 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 hypothesis basis. Like this is the best solution you can obtain once you have your neural networks. So this is the best one you may obtain. Then actually in when you use the computer to compute this one, and like you need to do the discretization. Like as we know, when we approximate a PDE, you need latitude points. And like for example, when you using the numerical integral, like you have like quadratic points. So this area is just quantify what how how well your discretization. So this is some kind of like when you have more and more latitude points, then you have a like the generalization area should be better and better. But on the other hand, when you have more and more, you have a lot of latitude points. This would be bring some difficulty in training your neural networks. Like this will bring some not a good thing in for the optimizations. Like uh, you have too much latitude points, and then you need to take more and more effect to training your neural network. So this two like some two kind of contradiction. So they have the competition between each other, these two areas. So people would like to say, I want to get a very good generalization area, but I don't want using too much latitude points. So this is actually the one of the main idea in our work. So we want to get a good area, and we want to get some very the stable or like efficient training process, but we can with a small number of latitude points. This is the basic idea for this is one of the basic idea in our this work. So then I will introduce this two, and this is so there are a lot of deep learning based method for PDEs like Ping, and we all famous Ping, or DTM or deep read, something like. So I will focus on Ping. So pings, like we all know, there's actually basically two kind of loss, like a loss of PDE and a loss of data. Like usually this one is fixed, and for loss of PDE, just as I said, you have if you that the number of latitude points is very important here. So actually, when you have more and more latitude points, you can get a better accuracy. So this is your better generalization area. So this is but actually when you too much, like you have too much latitude points, then it would give give some difficulty in training your neural network. So this is a contradiction. So I will skip this one. I will give some. So for ping, we all know it has some advantages. Like for example, it's like very easy coding. Like this is very friendly for student, for even for undergraduate student. And this is kind of methodist method. And and actually, I most like the pings. Like this is very good for inverse problem. I think this is one of the main advantage in for using pings to using ping for solving the inverse problem. And another advantage is like you is the advantage of neural networks deep learning, so it can solve high dimension. So this is some kind of the advantages. So for the disadvantage is like ping actually is, I mean, currently it's not very good for forward problem. Maybe like later something as more and more more people studying pings, maybe this would not be a problem. But uh, currently this is not a very, I think ping is not very good for forward problem, especially for like low dimension problem. So this is so another advantage is for auto differentiation. Actually, for auto differentiation, it has advantages. It also has disadvantages. So for advantages now, for when you're using auto differentiations, like this is also make you very easy to coding. And when you're using this auto differentiation, there's no discretization area when computer derivatives. So there's no discretization area. So this is a good thing. But the bad things, like in practice, I think maybe some of you already know this one is actually not very efficient to compute the derivatives. So when you have like second order PDEs, and you using auto differentiation to compute the derivatives. This actually would take most. This would cost most of the time, like maybe 87 to 90% of your total time in computing the derivatives. So this is not very efficient. So uh, because using the backpropagation. So this is it comes from the experience of the practice. So so this is also another motivation. So we don't want to use too much. We don't want to use too much latitude points because when you compute the loss of PDEs, like you actually the you need to compute the derivatives. So and and like if we have too much latitude point, and this would be like you it would cost you the computational cost is very expensive actually here. So here is the main issue. So another another point we want using we as less as we don't want to use too much data point is here. It's like we this because the auto differentiation is not very efficient. So here, so this is another motivation to we want to using we don't want to use too much latitude point. So this would like improve the efficiency when you're using a small number of latitude points. So this is the second motivations like here. So so then what I the main problem that I do is like I want to using ping, like using this kind of problem to solve the problem which has some kind of which have which has the sharp interface. So actually when you approximate problem with sharp interface like a large gradient is actually not very easy to using neural network to approximate such kind of problem. Actually, not only neural networks, but also like but also the classical approximation, like you using polynomial approximation, like Fourier approximation. All these kind of approximations not good to solve problem with sharp interface. So this is not the issue. This is actually a common issue. This is kind of common issue. So this, for example, this kind of problem. So then I want to use this one to solve like this kind of sharp solution problem. For example, like we all know, it's like a Burke's equation. Even you have a smooth initial condition, and as the time goes, you may have a very sharp interface problem. So something also like Navier-Stokes equation with a very very high nearest number. So this kind of problem. So even for like even using the classical CFD, like you using CFD to compute this kind of problem, this is also very expensive actually. So this kind of the problem I want to solve. So actually for classical numerical method, there's a lot of kind like using spectral, like you can design special specific function. You can using refinement. You can using moving method. I will skip this one. So so for ping, like for using pings to solve this kind of problem, all most of the method the existed methods like using adaptive. Most of the methods using adaptive, like I think this is Lulu's work, like let's do gradient. This is our yeah, this is our work, like the original in the some review paper, and I think this is the Lulu's work, like using the gradient of residue to adaptive to adapt sampling. These two are adapt sampling, and this also adapt sampling. And this work is done by Sto Tao. I also he's from CAS. He using the failure-informed adaptive sampling method. Also, like some kind of this is all adapt sampling, and this is like using adaptive weight, you some kind of like self-adaptive pings, like you have a weight in each term of the you multiply by a weight in here. Also, this is by Ameya also did a lot of work like using adaptive active function. Also, there's some kind of like dynamic weights, something like that. So all these methods are based on adaptive, like, but using this adaptive method is like maybe it's actually not very stable, also not very so efficient. So this, I just list some of them. So, okay, so then I will introduce a little bit deep ONet. So deep ONet, so I think there are different kind of operator learning for PDEs like deep ONet, like GNO, FNO, like PDEnet by Dongbin. So I think all of you very familiar with this one. So I just very quickly introduce this one, like based on this universal approximation theory. So I think this is Lulu developed this deep ONet. So I just skip this one. So so this is the deep ONet. Deep ONet actually is basically based on the data. So actually this is also deep ONet is also works well for smooth problem. Like when you do for the smooth problem, deep ONet works very well. And actually also the FNO like GNO. But for the problem with sharpness, actually, uh, I think I know DeepNet is better. DeepNet is better than FNO, like something like that. But it still have some problems. Like when you're using DeepNet, when you're using the data, you you may using more data, like you have more data along the shock, like along the sharp. So this is based on you have a prior knowledge to where the sharpness look where the location of the sharpness. So another example is like by like some kind of special mesh. This is also non-uniform mesh actually. So so I think most important is that for the for this kind of sharp interface problem, it's not very easy to obtain the data. Actually, because deep ONet, like all this kind of operator learning is based on the data you obtain. So actually, the the basic things like the data you cannot get a lot of data. So this is the I think the most important for this kind of problem. So so this is the for operator learning. So then next one, I will introduce the basic idea of my work. So then why are you using this kind of problem? I will just give an example. So for I, the idea is actually from the classical methods, like for your this kind of hyperbolic equation. So I know this is a hyperbolic equation. So actually for this problem, the solution for this problem is not unique. Even the weak solution is not even the weak solution is not unique. So from the mathematical point of view, so how people obtain a unique solution, like from the point of view of analysis, like we will add some viscosity here, and when you add the viscosity here, and you let the viscosity goes to zero, and then the solution, this kind of solution you can obtain. Is unique. Like when you add the viscosity, you can get a unique solution, and that the mu goes to zero. Then you can get a unique weak entropy solution. This is the solution satisfying the entropy condition. And this is the physical solution. So this is from the point of view of analysis, like from the continuum point of view. So based on this kind of analysis, like people, I mean, numerically, we can also use this kind of method to solve these hyperbolic equations. Like we can add some artificial viscosity, like we can add a very small viscosity and to to solve this kind of problem. And another thing, like you can also using the spectral SVV. I think this is spectral vanishing viscosity, and you can also by add the entropy viscosity. So so all this method is the basic idea is like you want to solve a relative easy problem, because if you directly, I mean, if you directly solve this hyperbolic equation, this is very actually. I know there's a lot of work to done for this one. But actually, it's still very difficult to design a uh, very nice method, like high order method. So it's very also not very easy to coding, like for the, I think Professor Xu did a lot of work on this one. So another very another class of method is like you want using this based on this idea. So based on this idea, so actually this kind of idea already being used for Ping. I think this is Zhang. Zhang was already using this kind of idea for Ping. And I think he already published 2 papers. I think this is the first one, and the second one I think is also online. So, but the problem for this kind of method, actually the numerical method, numerical solution, like is actually not the it's not the approximation of the solution of the original problem. So because we solved it, the problem we solved here is not the original problem. So this may bring some errors. Like you have actually you have the viscosity solution. So this is the idea of the classical method. So what I learned from this one is that we can we can solve at least we I mean for this kind of uh, problem with viscosity, like if you have some large viscosity, this kind of problem you can very easy to solve. So you can solve a bunch of this classical of this kind of method. And this kind of smooth problem, you can solve this. You can very easy to solve. And using this kind of using the data, I mean using the data of smooth problem, and you can learn that you can using operator learning to build a depot net, and then uh, you can using this kind of smooth problem to approximate the non-smooth problem. So I will just to here, let's give a more clearly explain here. Like here, I would like to solve a classical of smooth problem to first solve a classical smooth problem and obtain the data, and the training this kind of smooth problem using deep ONet. It's like we can using a very large, we can using relatively large new, like we can using relatively large viscosity. So, and this kind of problem is, you can see this is some kind of very smooth. So, and you can solve it in a high accuracy. So this is, you can pre-train this deep ONet. Then when you solve then you have a new case, and the new case is the sharp interface problem, means the sharp problem, and for the new case, and you can take the input here, and you can obtain this one, and now this is actually some kind of extrapolation of the deep net. Usually this one is not very, this is a very lot, it's not a very good approximation for the problem, but it's so we can then we can do a slight modification for this expression. So then we can do a slight modification. We can add some neural network, put this U delta as the input of a neural network, and the output is some kind of is some of the objective we want. So another thing is like the solution here is another thing we can use the ping. Another neural network is the same as the ping. So we want these two output, like the output of ping and the output of this U operator. So we want these two to be converged. So we want these two solution, like U operator and this U ping. We want these two solution to be equal. Like we want these two solutions to converge. So we can serve this one as additional loss. So this is additional loss in the training. So we can see the loss function. So see here, for the loss function, the first two term is the loss function of ping, like loss data and the loss PDE. So this is the loss function of the pings. And now we have an additional loss. So what kind of this additional loss? This additional loss is we want this two output to be equal. So this is the additional loss. So you can see that this is kind of, if you set lambda equal to 0, if you set lambda equal to 0, this is actually the ping. This is the original ping, and this can be used for like some kind of smooth problem. And so for the sharp interface problem, we add this term here. You can think this one some kind of like additional regularization. You can see some kind of this is additional regularization. This kind of regularization can improve the stability and the efficiency of the training process. So this is also, in principle, this kind of like meta learning with fine tuning, like because this operator learning, is some kind of meta learning. So you can big now like we all know ChatGPT, the big model, like this kind of meta learning, then with fine tuning. So this is some kind of fine tuning here. So 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 this is the basic idea of our methods. So so by so I will give some
Oh,
brief. Okay,
this is Lulu. I have one question for your method.
sure.
Um, so the depot net is pre-trained. That's clear. Then how about the second network, the NN?
So we
So pre-trained
both
or
work are needed. Both work needed to be trained. Need trained. So we train both work.
you mean you train the ping and the NN together
Yes,
simultaneously?
yes. We train two neural networks.
Oh, I see. Okay.
Yeah,
Then
yeah. We train. Yeah. You're right. Yeah, we. This is a neural network to be trained. This is also a network to be trained. So we train two neural networks.
okay. Thank you.
Mhm. So, so this kind of method can, as we'll see, so we don't need too much
Sorry,
latitude
can I have a
points.
question from
Sure.
previous slide? Sorry for that. Here, for example, for training deep on it, we consider different functions, different F for training deep on it, and then we will have different solutions here.
I'm sorry.
For training deep on it, we will have different functions F for
Yes.
training deep on it. And so we will have different solution from deep on it.
Yes.
And then I'm not sure about this network. I'm not sure what this network does, but how we can compare the output of pins and the output of this network, and to make sure they are like from same, for example, initial condition, or how we can compare
Yeah.
them.
So yeah, I think okay. So I mean, once you have a pre-trained deploy net, and then we can solve a new cases. Like for the new cases, we have a same input for deploy net, and this is same for the ping. So this is, I mean, X here and X here actually are the same. I mean, they are for the same cases. These two X's.
It means that first you train deep on it, and then it's like considering just test case or one special case for
Yes,
training.
yes,
Okay,
yes. Like
it's
this is kind of new test case.
yes, yeah, got it. Thank you.
Yeah. But this new test cases is not in the training spaces of the depot net. So this
Yeah.
is kind of extrapolation. This is not integration.
Yes, yeah, got it. Thank you.
Okay, so by using this method, actually, I don't need too much like latitude points. This is what I originally want to use that. So I can use a very small number of latitude points to get a very, I mean the accuracy is also very nice, I think. So the generalization abilities, like is the generalization errors can be significantly improved. So this is the first advantage. And the second one is like since we don't use too much latitude points, so the efficiencies can be it's very efficient to training the neural networks. And the third one is this, the training process is very robust because actually we can see this, you can treat this one as like some kind of regularization. So actually the training process is very robust. And more interesting is like we can use in this kind of problem to solve kind of yield-post problem. What kind of yield-post problems? Like with for some problem, I mean for the test case here, we may don't using the full boundary conditions. We can use partial boundary conditions. I will show you later. So this is why I solve this kind of problem, because if you remember, I originally said ping is not not a very good tool to solve the inverse problem. So then I want to solve some kind of inverse problem. So this is the sum of the motivation to
Excuse
solve
me.
this kind of. Okay.
Excuse me for interruption. I think Varun have a question.
Hi, Zhiping. I had a question on your previous slide. It's just like a clarification.
Okay, sure.
This is Varun from Brown. So when you say like data loss, how is that data being generated?
You mean this one?
Yeah, can you clarify just like my
This
understanding?
kind of this is the loss of the ping. I can, like, for example, if you solve the forward problem, you can think this one is actually the like initial and the boundary condition.
Oh, I see. Okay, so it's
Yeah,
just like
this is some kind of data you already have.
I see. Okay.
Yeah.
Yeah. Thank you.
Okay, so next, let me show you some numerical examples. So the first one is the Burke's equation. As we know, like this viscosity, if this viscosity is big, then the solution is very smooth, actually. And when nu is very small, or like nu equal to 0, I mean, eventually the solution is very sharp, like here. So for our first example, I will show. So first, I would like to train the new DeepONet, like the operator, by using a very relatively large viscosity, like from 0.02 to 0.06 over pi. So this is nu, is relative area, and the solution you can using these parameters like to training the DeepONet. And then eventually I want to solve the problem for like very small viscosity, like nu is like 0.001 over pi, or even invested case like nu equal to 0. So like for this example, I using like it's about 300 latitude point for this equation. See here, actually, I mean, if you, I mean, even for a smooth problem, if you use this small number of latitude points, you cannot obtain a very good accuracy actually. So usually you may need like thousand or like thousands of latitude points. So this is the results for this. The left one is for nu is small. This is for the inverse nu equal to 0. This is for the investigated case. See, if you for the original pin, is the latter one is the original pin. Like if you're using small number of latitude points, you cannot obtain a very, like this is the solution here is wrong here. And this one, I mean, this yellow one is the extrapolation of the DeepONet. And this one is the output of the operators, like, I mean this one. So, and this green one is this is the output of ping. Like here we can see, this solution is very good. I mean, also there's some kind of exciting result here. We don't have oscillation here. I don't know why there's no oscillation here, but this is a good result. So we also show the relative area relative L2 error here. Like this is for the vanilla pin. If you select use pin, the error is very large. And this is the expiration. I mean, and this is the output of the two neural networks, as just as Lulu asked. Like there are two outputs actually we can use here, and we can see that if both cases we can get some kind of very good result. And this is the, I mean, this one is the standard deviation of the error. So this we can see, this indicates that the training process is very stable. You can see it's very stable because the standard deviation of the error is very small. And also we train a case as the trainer case. Here we don't use the bottom.
Zhiping, how many points? I think you use very few, 6 points. How many points you use for pins? Did you say that?
For pins, here it's like 31 plus.
Oh, 31 points in space. Okay.
Yeah. So it's like, I mean, from -1 to 1, it's like about 30. And from, this is for time, 10 is for time.
Yeah.
Can I
So,
ask a question?
sure.
Yeah, this is Kamal from Brown. The previous slide,
Which slide?
wherever you are showing 31 into 10 data points.
Okay.
So yeah, so in this case, what is the network size in after the TPONet? So is it taking 1 point or
Sorry.
what is the network size after the TPONet? The small network size.
Okay, you mean network size for the,
Yeah.
mean for this
Yes,
one?
and then yes.
It's a good question. Actually, the size of this neural network is very small. You cannot you cannot use a very large size of the neural network here. So
No, what I'm asking is it like how many the input layer is how many? It's like because X and T
okay,
both
you
are
mean
there. So
like how many data for this one term? Like
no, in the network, the small network, what is the input layer size? Is it 1 or 2? Because you have X and T, but DeepNet will give you as a function. So what is the input layer size?
you mean input layer size. This is like this is the trunk. This is for the trunk net. This is the trunk net. This is for branch net.
Yes. So no, the smaller NN. So how
You
is
mean
it
for
like
this
from the?
one?
Yes,
Okay,
exactly. So
this one the input like I don't remember, but this is the dimension of this utilica, like
so
the
that's a
input layer.
complete function. Complete function. So the
Yeah.
next network is
This, I mean, the input of this neural network is this
yes.
utilica. This is a function.
Yeah, so that will have a lot of points. So the first layer is like
That's no problem. That's no problem because actually when you compute this term, it's very efficient to compute this term because you don't need to compute any kind of derivatives for this. I mean for this additional term. So you can use a very large number of points for this term. Actually, this doesn't affect the efficiency here.
Okay, thank you.
Hi, my name is Vivek and I'm a PhD student working with George. Can I please ask one question here?
Mm-hmm.
So, if I understand correctly, for the Burgers equation, while pre-training the DeepNet, you are using the viscosity as the input to the branch net. Correct?
Yeah.
So,
Yeah.
yeah. Yes, so I was wondering how difficult or how easier it would be, suppose if the problem formulation was as such that you were trying for different initial conditions rather than just the different viscosities which you have considered here. Have you considered?
Here are using the same initial condition, but with a different viscosity.
I understand. So I was wondering if you have tried the other way around, like same viscosity but different initial condition, random initial condition.
It's good question. This is the what I did next.
Oh, great. Thank you.
Yeah. This is the prediction for unseen t. It's like for like I fixed the viscosity here. In this case, I fixed the viscosity, and as we know that if you have a very smooth initial condition, and as the time goes, and actually the final solution is very sharp. So I can using using the solution for t in 0 to 6.6, and the solution here is very smooth actually, and then you can use this kind of smooth solution to predict for the case t, like for a large time t, like t in 6.6 to 0.8, and so yeah, this is, I think this is what your question. Yeah. So same thing, like for the latitude point for ping, like from -1 to 1, I using like 31, and like for the time t from 0.6 to 0.8, I using 3. It's this kind of uniform mesh. So almost the same result we can obtain, like here. Like this latter one is the one using the vanilla pin, like the original pin.
Yep.
And this is the expression, and this is this green one is the output of pin. So our method. So
thank you.
So again, like I show the relative area here for Box equation. So this is for the vanilla pin, this is for extraction, and this is for the two output of the neural networks. So this is for the Box equation. So also I solve the cavity flow here. So I just solve the steady state problem. So also I learned from George and Zhicheng's paper. No, actually for the steady state, actually the solution is not unique. So actually in our method, we also can get the right solution. I mean, right physical solution here for the steady state. So I trade two cases. Like I using two methods. The first, for the divergent free condition, I using hard constraint or soft constraint. For the hard constraint, I using the method used I think in Materials paper, the original paper, I using this vortex thing. And if I using the soft constraint, I just put this term as additional equation. So there's two methods here. So let's first show for the soft constraint for divergent free condition. So for the cavity flow, the first one I using like for latest number is from 400 to like 700. So this small latest numbers like high viscosity, and then I using this deep ONet, this pre-trained deep ONet to solve the problem for latest number equal to 1,000. So here, I mean, for this cases, if I using soft constraint, I need like 10,000 uniform distributed, like 100 multiplied by 100 latitude points for pin. So let's compare the one by Zhicheng, like he used like 40,000 latitude points. So here. So this is the reference solution. So if we're using the vanilla pin, we cannot get the right solution. So but using our methods like here, this is the two outputs of the two neural networks. Like usually, I mean, for this case, for cavity floor, the output of pin is better. Like here, we can learn the vertex here. So this is for the soft constraint for the divergence-free condition. Actually, this is not very very promising, not very good. So if we use the hard constraint for divergence-free condition, I solve the same problem. Like for same problem, now we can see we only using like about 900 latitude points for pin. I mean, like 30 multiplied by 30, like 30 by 30 latitude points. So this is only 900 uniform distributed latitude point for pin. So this is a very, very small number of latitude points. So like, for example, as again, like I know in Zhicheng's work, they're using actually like about 40,000. Like this is not a, this compared to this one, like it's very, very small number of latitude points here. And we can see, so this is the reference solution. And this, again, this is the two output of the trained neural networks. We can see, again, we can still learn the vertex here, like these two vertex, see here. So this is for the hard constraint for the divergence-free condition. So I also show the relative area for the velocity here. It's like, see here, this is the area, and this is vanilla pin, and this is the extraporation. We can see this is for the output of our pin. Like see the relative area is all very small. It's like smaller than like 5% here. So I also show a case if I don't use the left boundary, like for this example, I don't use the left example. Okay. So see here, if we don't have the left boundary, we can still get that good solution. This is the one I don't use the left and the button. So boundary condition, I kick out two boundary conditions. So this is one I kick out one boundary. This is I kick out two boundaries. So see, if I kick out two boundaries, it's still not too bad, but here the vertex here is not so nice. So again, I want to focus on only like 900 like latitude point is used. So so this is so after I read the paper, actually I also, this is the relative area, so I skip this one. I did some more tests. This is some kind of a new test not included in the paper. So so as we see here, like for the Dylan's number is small, like here, if like it's smaller than like 1,000, there's no vertex here. I mean no vertex here. No vertex here. But when the Dylan's number is like in 2,000, we have vertex here. So this is the reference solution for Dylan's number is like 2,000. See here, we have new vertex here. Not only these two, but we have the third one. This is the third vertex is here. So my question is like, if can we use this kind of method to learn this new vertex here? Because for the deep ONet here, for the deep ONet, the Dylan's number is, for this one, if the Dylan's number is between 400 to 1,000, actually for this kind of problem, we cannot see any vertex here. I mean, even for Reynolds number is equal to 1000. But the idea is that can we use this kind of thing to predict something like some solution have a different character, like we have new vertex here. So this is the new test we did. So we can use this this data to train a deep neural net and to predict for the Reynolds number equal to 2000. See here, this is the solution of our pin. See here, we can learn this kind of new characters like here. Like we can list the third vertex here. So this is not, we cannot see this one for this deep neural net. So this is a new stuff thing, and also like for we can even predict solve the problem for Reynolds number equal to 3000. See here, we also can learn a third vertex here. So this is like from none to from 0 to 1. Like we can learn a new feature. We can learn this kind of new feature. So this is this two tests what I want to do. So finally, let me give a summary. So we just combine the operator learning and the pin. So to solve the problem with sharp solutions. So we use the operator learning to learn some kind of smooth problem, which is related to the sharp solutions. So finally, we use this pre-trained operator and the compiler pin to solve the sharp interface problem. So this kind of method is very stable and efficient. Also, the generalization average is very good. So we can also use this kind of problem to solve the problem without sufficiently boundary condition. So this is the thing. So my future works like if we can solve more complex problem, and we can use this kind of operator learning and combine some kind of classical solver. So this is what I feel to do. Okay, thank you.
Thank you for your great talk. So now we open the floor for questions. Are there any questions for the speaker from the audience?
Can I have a quick question?
Can you introduce
sure.
yourself first?
Yes,
Yeah, I know. We know each other very well.
Yeah, it's very good seeing you, Zhiping. That's a very nice presentation. So very quick question. So for the last problem that you showed, have you tried what is the maximum Reynolds number that you can extrapolate?
Yeah, good
Train?
question. Actually, I tried a Reynolds number equal to 5,000. Like for 5,000, we can we can learn this kind of new vertex here. But for 5,000, it's like less a small vertex here, but we cannot learn the vertex here. That's the fourth one. I cannot learn the fourth one. Also the relative error goes to bigger and bigger.
Okay. All right.
Yeah.
That's interesting that you can go all the way to 5,000 actually. That's great. Okay, thanks.
Mm-hmm.
So are there any questions?
I have a question. Thanks, Zhiping. I have a question for Lulu, if he is still there.
Yes, I'm here.
Lulu, what's in your paper reliable extrapolation?
Yes.
So you advocate you can use pins to let's take the extrapolation case that Mao is doing, let's say with a time or in Reynolds number. And so you sort of advocate that you can use pins as one of the methods to go further, let's say, in time or further in parameter space and so on. So, but you will be doing this serially, right? So you take the DeepNet prediction, and then you sort of improve it. Here he's doing it simultaneously. So what is the difference? Has anybody checked the difference?
Technically, one main difference is we have DeepNet, then we do basically transfer learning. We reuse this DeepNet, we fix the branch and then fine-tune the trunk. But here, GP basically add extra network.
Right.
Extra networks.
But you have the pin, right? You one of the methods you propose is to have the pin because you have the physics informed laws.
Yes.
For extrapolating, just like take the antiderivative example. Which one will give you because he's in some sense he's doing extrapolation.
Yes. So Lulu, so you did the second. You just train your trunk net, and the trunk net is satisfy the PDE. Am I right?
Yes. So basically, what we do, so in your
actually,
the loss function is similar. So we have a pre-trained DeepNet, and we fix the branch and then fine-tune the trunk.
Okay, I see. Actually, I mean, initially I won't use this kind of method. So actually, this is almost the same, but I think the one maybe the one issue of your method is that if you in the training, I mean, if you like using this kind of stochastic method for training, that's probably it's not very stable. If you modify your trunk net too much.
Yes. So for example, for this specific case, here you can use 900 points for training, but we cannot because we still use pin training. I mean, eventually become a pin. The 900
Yes, eventually actually this one is pin actually.
Yeah, but here you keep using DeepNet result. So you have actual regularization, which we do not have.
Yes,
that's why
yes,
actually the 900.
Actually, yes, the actual regularization is a good thing to stabilize the training process.
Yeah, this is actually a key for both problems because you can see he could solve the implicit Bergers. He could also solve the cavity problem for which you have singularities. So with zipping, we could not solve it because we not with Jincheng because we had the singularities. So when we added a viscosity term, that was a different way of regularizing. So we were actually getting the DNS result using an LES equation because we added the eddy viscosity term to go to higher Reynolds numbers. But yeah, I think it's a very practical way what zipping is doing.
So, are there any questions for the speaker?
May I ask a question? My name is
Yeah.
Satish.
Sure.
I'm from Brown. Yes. So if you have bifurcation, so what would happen if an instability happens? How would your method be able to extrapolate in those situations?
Sorry, can you say it again?
I mean, you are showing the steady state solution, meaning that there is no flow instability.
Yeah.
Right? And then
let me elaborate what Satish is saying for the cavity flow. So let's say the cavity flow in 2D becomes unsteady at Reynolds number 8,000. So let's say you use DeepNet up to, let's say, 6,000 to 7,000, right? Which is still steady.
Yeah.
But then you're trying to solve the flow at Reynolds number 9,000 or 8,500. So that the flow is unsteady. So the pin will be in the unsteady past the bifurcation.
I see.
But the depot net is in before the bifurcation. So this is actually, it's a Hopf bifurcation. So you can think of amplitude versus Reynolds number. It's like, it's like this. So you have I don't have my camera, but basically it doesn't matter. It's a Hopf bifurcation. It goes like zero amplitude, then goes like that, square root of Reynolds number. The amplitude goes with the square root of Reynolds number. So before and after the bifurcation, depot net is before, and then pins is right after the unsteady flow.
Yeah.
Have you tried that?
No, I didn't try. So that large Reynolds number.
A simpler example is to actually use the van der Pol oscillator that Satish is using for the flow also to change the bifurcation parameter mu.
I see.
And there you have you have limit cycles, but you have different frequencies. So you can see if you can go from one frequency to another. That's a very good example. Maybe Satish, we'll try it ourselves.
Okay.
Yeah.
I just thought about this, about the van der Pol example. It's simpler, but deceptively simple actually.
Okay.
Thank you.
Kamal, do you?
Yeah, I have a small query. How it work on the inverse problem with noisy data?
You mean for the inverse problem with what data?
With noisy data or real data?
With noise data. I think it's I think this method may be, I think one and a big one advantage is like it's much more stable, I think. Yeah, but since you have a noise data, I don't think maybe I cannot guarantee the accuracy, but I can guarantee the stability.
And I have one more query, like sizes wise. So if I put, how to decide the size? Like, is it any complementary? Have to be, because there's two network. So one may train faster the other one.
I mean the size of the two neural network.
Yeah. So because you have a network after the depot net and the one pin network. So
yeah, good. Yeah, this is a good question. So yeah, I mean, as I said, the network size for this neural network cannot be too big because you don't want change too much of the extrapolation of this utility. So the size of this neural network should be small. And I mean, then for this kind of for the size of ping is up to you. I don't. There's no. It's like as usual, like yeah. There's no guidelines for the size of pings. This is depends on what kind of problem you solve.
why I'm asking, like basically, is it overfit one network and the other network is not trained? Is it possible something like that?
Yeah, I mean, so if I understand it well, so actually, so when you training these two, when we train these two neural networks, actually, yeah, you can. There's some kind of balance. You can actually. So I mean, initially, these two neural networks should be like almost the same weights. But later, it's better to add weight for this kind of for this pin. Yeah.
Okay, thank you.
Because I mean, when you training after some epochs, like the may thing is this one would be better using pin is better. Like you can add weight for pin.
So that basically the control by the lambda.
Yes.
Okay, yeah, thank you.
Dr. Mao, I had just one more question. This is Vivek from Brown again. Can you please comment on the choice of the Reynolds number, for example, in the lid-driven cavity problem, the choice of Reynolds number for the pre-trained DeepONet? Why did you choose, let us say, 400 to 1000? What if it is just 1000 or, okay, yeah. The choice of Reynolds number for pre-training DeepONet. Can you?
Why I choose this kind of data?
Yes. What if it is larger range? What if it's a smaller range?
Yeah, there's no problem. It is just for test, for some kind of test. You can use once you have sufficient data, like you can use things like smaller number, like from 1000 to some kind of like 700 or 800 is not it's no problem. This is just for some kind of test.
Okay.
You can use it depends on the problem, and it depends on what kind of data you have. Yeah. Once like for example, it's just George said you have data from Linux number from 500 to like 5,000. You can using 500 to 5,000 for training the DeepONet. That's no problem.
Okay.
Once you have the data.
The reason why I asked was once the pre-training is done, I was wondering even if you just used 680, it could be okay because after you are pre-trained, the pre-trained network would be frozen, right? And so
yeah. If you do the interpolation, there's no need of all this stuff.
Yeah. Okay. Thank you.
So, do we have more questions from the audience? Thank you for your great presentation. I think it's time to move on to our second session. Yeah. Rui, Zhang, are you? Yeah. Thank you
Hi,
so much.
George.
You can stay here. We have.
I need to go. It's too late.
Okay.
Thank you.
Bye.
Rui, are you there? Can you hear me?
Yes. Can you hear me?
Yes. Thank you so much for joining us today. Can you share your screen to see if there is any problem with sharing or not?
Sure. Can you see my screen?
Yes. Thank you so much. Okay. Our second speaker is Rui Zhang. He will be giving a talk on physics-informed parallel neural networks with self-adaptive loss weighting for the identification of structural systems. Rui Zhang is a PhD candidate in civil engineering at Penn State University, majoring in structural engineering and mechanics. His research focuses on the development and application of physics-informed machine learning to solve structural identification problems. With that, we invite Zhang to begin his presentation.
Thank you. Thank you, everyone, and thank you for the introduction. So my name is Ray, and it is a great honor for me to be here at the Crunch Group seminar at the Brown University, so the home of the Penn and the DeepONet. So today I'm very glad to present my work, which to develop and apply Penn's best method to solve the inverse problem, particularly in the structure systems. So please feel free to unmute yourself if you have any questions. And before I get into the methodology, I'd like to have a brief review of my research background. So as you know, the structure identification is being a typical input and output system. So the general idea of the structure identification is try to, from the vibration data, which is from the sensor network of a structure, and put this as an input to estimate the structure parameters and to detect the structural damage as the output for the final structural condition assessment and the decision making. So the key here is structure identification approaches. And depending on whether we know a physics model or not, it can be divided into two approaches. The first one is physics model based, which means we have a particular like a finite element model, or we have general governing equations, and then we can based on this physics model to do the identification problem. And another one is we don't know exactly physics, so we can use some like in the time domain or the frequency domain methodology, or using the machine learning methodology to try to identify the damage. And both two methodologies have some disadvantages. Firstly, for the physics model-based methodology, for example, we usually using finite element modeling and update the structures with the damage. So we try to minimize the residuals between the measurements and the simulated results. So if we are required frequently and repetitive model updating, so it can be computationally expensive. And also as a mesh-based approach, the finite element modeling will have some the truncation errors and the numerical errors of the variational forms. So also if we have a model governed by the general structure in the form of the PDEs or the ODEs, so it just looks like a physics model-based discovery problem. So we need to identify the unknown parameters. And for the machine learning-based approach, the general idea is it can transform the identification problem to a statistic pattern recognition problem. So right now we don't have any accurate physics model. So a popular way is to using the machine learning to mapping the input and output. But the application of the black box models, which means we don't have physics, important physics information in that. So there are a lot of research has been conducted in this field to improve both these two approaches. And recently, a very inspiring thing is a methodology called the physics-informed neural networks, the PINs, are developed which are used for solving the inverse problem and also the forward problem. And particularly for the forward problem, it shows a huge benefit. So the motivation right here is, can we use the PIN works into the areas of the structure identification? And if so, how it may work? So I assume that everybody is familiar with the PINs. So let me just have a quick introduction of the main idea of the PINs, and also to clarify some notations, particularly for the inverse problem. So this is a basic architecture of the neural network, which is mapping the input layers X and the T, and also the output mu. So with the help of the automatic differentiation, the derivations of the output mu with back to the input vectors can be obtained and then assembled into the loss function. So for example, this is a PDE function. So I use FGE represents the governing equations as a PDE as an example, and the X is the input, the theta is the parameters of the neural network. So the mu with the head is a prediction from the neural network, and the gamma is a unknown structural parameters. And particularly, I treat the PDE residue as training error epsilon GE. And then we can express the loss function, which is a mean square error. And I introduce 1 divided by 2 just for the expression simplifies. And in that case, the loss function can be expressed as a vector expression. So it can be expressed by the NGE inverse. NGE represents the number of the training dataset in the governing equations domain, and the epsilon GE, which is a vector of the training error. So for example, when we have the input XGE for this particular loss terms, it is a column vector, and the column number is NGE, and the second for the row is 2 rows, which means the input is X and the T. So with the input, we can get the output, and it is only a column vector. And then the training error, it is also a column vector. And then the loss function, the LGE, will be a scalar. So with this expressions, just to simplify, and then we get the governing equation, right? And also the boundary conditions. And this two part is physics informed. And particularly for the inverse problem, we assume that we don't know the initial condition. So we have some sensor data, for example, and then for the sensor data, again, the epsilon S represents the training error between the prediction, the mu hat, and the measurements, which is the mu. And then we get the total loss. This is the physics, and this is the loss, and then we get the total loss. So in this case, we use a simplified expression to represent the total loss. And the epsilon right here is a training training error, which include all the training errors respect to each input. And the N, which represent all the bench size of the training input data. So in that case, we get the total loss, and then we can update the unknown parameters of the neural network and also the unknown parameters of the structure by minimize the total loss. So the general idea of the PIN, particularly for inverse problem, can be shown in this diagram. So for the goal of the presentation is we try to apply and try to demonstrate developed PIN's parallel neural network framework for solving the identification problem, particularly in the structure system. So let's use a very simple, typical structure system as an example, which is a beam. So in this spindle, we can find it has a multiple span continuous beam with an external force. And we have some boundary conditions at the internal and also at the boundaries. So this is the governing equations. The M represents the mass, C is a damping, EI is flexure rigidity, and the P is external force. So generally, this is entire computational domain, which is covered by the total a single PD. However, particularly for this case, we can find we have some structural discontinuities, which means for each span, the dimensions, the loading, the probabilities may be different. And also we have some internal supports, which means solving a single PDE in an entire domain will be not very feasible. So that's why we're using the domain decomposition, which is also a great way to handle the discontinuities. And like it is just like the XPINs, which is developed by your research group. So in this case, we will divide the whole domain as several subdomains. And for each subdomain, it should satisfy the corresponding governing equations. I call it as the GE, which is a PDE function. And also it should satisfy the boundary conditions at the first support and also the last support. And also you need to satisfy the brown one, which represents the interface physics. So which means all the points at this internal supports should satisfy this interface physics. Okay, so this is about the physics of this beam. But for the inverse problem, some structural parameters may be unknown. For example, the flexure rigidity of each span is unknown.
Rui, can I see the interface conditions that you impose?
Yeah. So for the interface physics, it has different equations. The first equation is about the deflection, which means at this point, the deflection as the adjacent from two subdomains should be the same. And the second equation is about the slope, which means at this point, the slope as the two adjacent domains should be the match. And the last two is about the balance of the force and the shear and the moment. This is a particular for the beam problem.
Yeah, these are good. Instead of, you could have done the residual continuity But this way it's you have the lower derivatives, which is the proper ones. Yeah.
Yes, exactly. Thank you. Okay, so right now we have, for the inverse problem, we have some incomplete physics information. So we need more, which means we need the data. So that's why we put some sensors. For example, we put the sensors on each span of the beam, and then we can collect some data. For example, the accelerations, or it can be the deflection or the strength, it doesn't matter. So in that case, we can also represent the sensor data as a dotted line in the computational domain. So now we have the incomplete physics, and also we have the sensor data. Now the goal is we try to predict the unknown parameters, and at the same time, we try to predict the full state of the systems based on the limited and the noisy sensor data, which is just locally installed. So this is generally a problem statement of the research. And as we know, for some particular case, if we have a longer time domain or have some discontinuities also along the t dimensions, we can also divide the entire domain in both space and the time dimensions. So again, we use the typical computational domain as an example to show how to apply the pins on the beam structures. So we select two subdomains as an example to solve a system of the PDEs. For each subdomain, we need to assign a neural network to solve an individual PDE, and the input will be the space and the time variables, the x and the t, and the output is the deflection mu. So then we use differential automatic differentiation to get the derivatives. So again, we need to use some input as a training data sets. The first input as an example is input xg, which represents the input from the domain for the governing equations. And for this kind of the input, it should satisfy the PDEs. And also we have the data from the sensor, and it should fit in the data. And again, for the second domain, the data should satisfy the governing equations and also the sensor data. And again, these two inputs are different. And again, to connect these two neural networks, we need to use the input as the interface. So which means all the points are at the interface, and they are also belong with two adjacent subdomains. So which means during the training process, the input should integrate to two adjacent neural networks, and it should satisfy the interface physics along the time t. So with that equations, we can get the total training errors along the whole domain. And then we combine it into a training error vector. And then we can get the total loss. And as we know, there are a lot of the subdomains, which means we introduce a lot of the lot of loss components. So that's important for us to determine the weight for each loss component. And then we can get a weighted loss. The general idea is right now we can update the parameter theta and the gamma by minimize the weighted loss function. So previously we determined the beta by using some of the hand tuning, but right now we will propose a different way, which is based on the NTK theory, which can be a self-weighting. So the general idea is how to determine the weights for each loss component. As we know, there are different strategies to determine the weights, including various adaptive methodologies. And particularly, we try to use self-adaptive weights, which is inspired by the NTK methodology. And particularly, we extend this methodology, particularly for the inverse problem. So I will try to improve it step by step. So as we know,
I have a query on the previous slide. This is come out from Brown. Previous slide. So each subdomain has a network, or each degrees of freedom has a network.
Sorry, can you repeat for the subdomains problem?
Each subdomain has a individual network, or each degrees of freedom has an individual network.
Yes, it doesn't have an individual neural network for the interface, but for each subdomain, we will install an individual neural network, and which is totally different with the different settings. They are training independently.
What I'm saying, like, it is the domain has a network, or it's the each degree of freedom of that system has individual network. So in the domain you might have more degrees of freedom also, like displacement in X and Y. So they have different network, or
sorry, I'm not sure I capture all your questions. Do you mean for each subdomain it will have different freedom?
Yeah, so each node may have different 6 degrees of freedom, correct?
Oh, sorry. For the beam problem, we use a continuous structure system. So we only use one single PDE to represent the entire span of the beam. So each beam use one PDE function.
So each node may have a deflection and a rotation. So 2 degrees of freedom.
Yeah, I agree with you. So for the ODE problem, it will have several degree of the freedom. But for the PDE problem, we only it is infinite SDOF. So in that condition, we just use one single PDE to represent the entire beam. So in that case, we don't need to consider the degree of the freedom. It is just a single PDE. But if you discretize the PDE to the ODE function, you will have several DOF. So in that case, you need to represent each degree of the freedom. But we don't use that way. We try to solve the PDE in strong form.
Okay, now it's okay. Thank you.
Thank you.
Rui, since you are on this plot, can you go over the I missed the continuity conditions in time in that yellow? Yeah.
Oh yeah. Sorry for this particular case. There is no continuity along the time t, because I just tried to explain a general idea. But after I present this general framework, I will present an example. For that example, you can find all the equations along the x and also along the t.
But you have this equation in orange in the next slide. In the next I think, where you have this.
Yes.
Maybe next. Yeah, here.
Oh yeah, I got it. Yeah.
Yeah. So this, or what does this say? You impose.
Okay. Yeah. So I just use a very, how to say, a general equations. But the general idea is at this interface of the time t, which is the state should be the same, which means the deflection along the deflection, velocity, and the accelerations should be the same.
I see. So the states and the accelerations.
Yes, exactly.
Sure. Okay. Sure.
Thank you. So yeah, to simplify for the framework, I just use a general equation, so it is not very clear. Thank you for the question. Okay, so from now on, I will try to analyze and to develop the weights of for the loss components. So as we know, for the PIP's framework, the loss function will have multiple loss components. So we use gradient descent, try to update the theta, which is from the neural network, and also the gamma, which is from the unknown structural parameters. And the neta is a learning rate. So if we rearrange these two equations, we can find the dynamics of the weights can be looks like a limit when the nifty is very small, and then it can be represented as a negative gradient of the loss function respect to the parameter theta. So, and then we can substitute the loss function into this equation, and then we can get this kind of the equations. And again, we can calculate the dynamics of the waves for the particular parameters gamma. So with these two parts, we can analyze the error changing rate during the training, which means we try to analyze the change of the error epsilon. So by using the chain rule, we can find the derivative of the epsilon with respect to the time t should include two parts. One is including the parameter theta, and another is the parameters gamma, which from the unknown structure parameters. So with two parts, which means the training error evolution will not only consider about the neural network, but also consider about the structural systems. So in that case, we put these two equations, and then we can get the total equation. And again, we put this together and define this part as a kernel. Excuse me. So in that case, the kernel K will represent the evolution of the training error epsilon respect to the parameter theta and also the parameters gamma. So in that case, the NTK matrix can be considered not only the neural network, but also the structure. So right now we get the kernel, but how to get the weight? So we need to look more details and deeper on this equation. So as we know, the training error is a very simple ODE function governed by this equation. So the beta is a weight, the n is a bench size, and the k is a kernel. So we can find the k is just like a slope, which represents the k can govern the evolution of the training errors. So we can solve this ODE very simply. Oh, sorry. And again, the k can be deposed by using the eigenvalues. So in that case, the k can be expressed by the q multiplies the n with the q transpose. And the lambda is a diagonal matrix, which is the elements of the diagonal line will be the eigenvalues of the k. So from this ODE and from these solutions, we can find if the NTK has a larger value, which means has a larger eigenvalues, it will be decay or it will be converged very fast. But if it has a smaller one, it will be converged relatively slowly. But we have multiple loss components, which means different loss components maybe will have different NTK kernels. So which means we try to balance by adjust the kernel eigenvalues for each loss component. So before that, I will define a term called the convergence rate. So from these equations, we can find the convergence rate can be the mean of all the eigenvalues. So the lambda, the trace of the lambda will be the sum of the eigenvalues, and the n inverse can be the mean, and the beta is used to adjust the convergence rate. So and also the trace of the k itself will be equals the trace of the eigenvalues. So the eigenvalues here can be determine how faster the training errors decreased. So the general idea is when we got the convergence rate, we need to adjust the convergence rate of each loss components. And I make a small finger to show the general process. And the dot blue line represent the convergence rate of each loss component. And the black one, the black solid one will be the equivalent convergence rate of the total loss. So what we try to do is, as we know, each loss component will have different convergence rate. So we try to assign a beta for each loss component and try to make sure all the loss components are converging in the same pace, just like the equivalent convergence rate of the total loss function. So in that case, we can determine the weights, which is a function by solving these equations, the last equations, and it is a function of the trace of the total kernel divided by the kernel for the particular loss terms. So in that case, we get the NTK matrix firstly, and based on the NTK matrix, we can get the weight. So the key LL represent the element on the L row and the L column, which is on the diagonal of the total NTK matrix. And it represents the kernel for the L loss component. So in that case, we can determine the NTK weights. So this is a general procedure how to calculate and determine the NTK-based self-adaptive weights. And the general idea is we try to use these NTK-based weights to balance the convergence of each loss component. So this is the extended Penn's framework with NTK. And after that, we get a complete framework, and we can use a trained framework to predict the state. So right now we have get all the trained neural networks, and then we can sample it from the entire computational domain, and then put all the inputs into the training neural networks, and then we can get the deflection, which is the mu, and also the velocity, which is a derivative of the deflection with respect to the time t, and also get the accelerations. So for this part, we don't need to train the neural network. We just get the result directly. But it is based on the system is not changing. But if you have changing the boundary conditions or the loading conditions is changing, we need to retrain the neural networks in time. But right now, it's just like the transform learning. We have pre-trained the neural networks. And if we just change the boundary conditions, the retrain process will be much simpler and easier. So this is generally about the framework, how to, the general idea, how to develop the NTK-based weight and how to use and how to apply this on different structure system. And from now on, I will try to give some numerical examples. So depending on the time limit, I will try to focus on one example in details. And if time permit, we can have more insights on different examples. So the first example is about the stepped bar. The second is about the continuous beam. And the third one is about plant. So these three examples are very typical used in the structure systems. Okay, let's focus on a beam structure as an example. Oh, excuse me, I cannot. Oh, okay. So this is a 3-span continuous beam, which is under the moving vehicle load P with a velocity V. So we can find for each span, the flex rigidity is not the same. So we firstly get the computational domain of the beam. And the X represents the location, right? The Y represents the time T. So when the moving node is moving on the first span, okay, so the first span has some forced vibration. And at the same time, the other two span is under the free vibration, which means there is no external force. And when the moving node is moving on the second space, which means the second subdomain is forced vibration, and the other two are free vibration. And also when it is the same when he is moving on the third span. So the general idea is, for this particular case, we divide it by 9 subdomains. And for each subdomain, it will governed by a totally different PDEs. And also this is the boundary conditions at the first spot. and at the last support. And this is the continuity conditions along the X as the support. And also these two lines represent the continuity conditions along the time t. So for each subdomain, we will have the physics. For example, the continuity conditions. This is for the physics about the X. So we can find the deflection and also the slope, and also the, it is a moment right at the two supports should be the same. So this is the physics as the interface along the time X. And these three equations represent the interface physics along the time t, represents the deflection, the velocity, and the accelerations are the same as these two interface lines. And also for the inverse problem, we assume some parameters are unknown, which is a flexure rigidity for each span. So this yellow one, which is assumed unknown for this particular case. Okay, and then we're given the incomplete physics, and also we have some sensor data because we need more to identify the unknown parameters. And again, for the sensor data, we use accelerations as an input. And we simulate the accelerations by using some structural methodology, which is model analysis, and add some noise, which is white noise, to simulate the real world condition. And based on the incomplete physics and the sensor data, we try to determine the unknown parameters and also to predict the full state of the system based on the limited and noisy sensor data. So again, this is a problem statement. And the next step is we try to apply the Pen's work. So as we know, we have 9 subdomains, right? So for each subdomain, we assign a neural network. And this is the size of the neural network. It has 4 hidden layers. And for each hidden layer, we have 16 neurons. And right now, for this particular case, this is the loss functions, including the sensor data, governing equations, boundary conditions, and also the continuity conditions along the X and the T. So we know it is a lot for the loss components. And the training bench size for all the inputs is 128. So we know we get the loss function and the training bench size, and then we can calculate the NDK matrix. So we conduct all this in the Python. So I will ignore the process how to get the kernel in details. But generally, this is the NTK matrix. Because we have 90 components, which means the NTK matrix will be 19 multiplied 90. And for each element, it will be a matrix with a size of a square matrix with a size of 128 with 128, because the bench size for the input is 128. And the particular for this element on the diagonal will be the NTK matrix particular for each loss component. So when we get the NTK matrix, we can calculate the eigenvalues. So I use this finger to present the eigenvalues of the NTK matrix. So the X label is the list. Excuse me. The Y label is eigenvalues. So which means we get the kernel and we try to calculate the eigenvalues. This is the initial state, which is the time equals 0. And we calculate all the eigenvalues and order the eigenvalues from the largest one to the smallest one. So that's why all the figures are decreasing, because we reorder the eigenvalues. And we can find that during the training process, the eigenvalues of the NDK is look upward. And finally to the last step, which is black solid one. And for some cases, the NDK will be converged to the last step very well. But for some cases, it doesn't converge very well, but it is almost there, which means for this particular case, we assume that the NTK matrix is start to converge after like 50,000 iterations. So now we will focus on the last step to give more details, more information of the NTK matrix. So we get the eigenvalues of the NTK as the last step for the for the dot line. So the dot line, which is a K, right? And also we get the NTK matrix for each loss component. For example, the blue one is NTK for the governing equations as the 2-2 matrix. So we can find these three, the KGE 1, 1, 2, 2, and 3, 3 is the largest matrix with the largest eigenvalues. And these three are corresponding to the loss components of the governing equations as a diagonal, which is on the direction of the moving vehicle load, which means the force vibration has the largest NTK matrix, and it will converge faster than other loss components. Sometimes we like it, but sometimes it will make the convergence not imbalance. So that's why we introduce the self-weight. So we can find the GKE22 is almost match the total NTK matrix. So we assume that it is dominate the entire training process. So we got two key informations. One is about the kernel and another is about the convergence. So based on these equations we just proposed previously, we can get the weight, which is dynamic change along the time. So just like this information, it is almost converged up to 50,000 iterations, and then it is almost converged to like a very stable level. So with this adaptive weights, the next thing is, does it really improve the accuracy and of the framework? So the next step is we try to compare with the pins with or without the NTK. So firstly, let's compare the loss. The left finger is about the loss, which is the pin without the NTK metric, without the NTK weights. In the middle one is the pins with the NTK weights. And the other stating of the neural network, the optimized methodology is totally the same. And the third is a change of the loss. The blue one is initial loss, and the first column, the first three is the total loss, and the other 5 is loss components. And the red one is final loss with the pins, and this without the NTK. And the third orange one is PR pins with NTK. So the first interesting thing is we can find when we introduce the NTK weight, the final loss is increased compared to the PR pins without the NTK. It looks not good, but we can find the other four loss components, it decreased very well, very significantly. So we can also find this from the middle finger. We can find these 4 components are decreased significantly. So which means even we assign a small weight for the governing equations loss, which means for this loss, it will not converge very fast. But now we have a more balanced convergence rate, which means others can converge in a relatively better way. So that's why even the total loss isn't reduced, but the total performance is increased, which means a small loss is also does matter. So the second step is we can compare with the predictions. Firstly is identify the unknown structural parameters. So the second row is with the NTK, that's the adaptive weight. And the second row is all the weights are equals 1. You can find the neural network size is the same. The optimizer, the bench size is the same. But without the NTK, it cannot converge to the ground truth. And if you can find critically, you can find at the very beginning, the loss, the EI, the parameters is decreased very significantly and then try to converge to the ground truth, but they cannot converge to the ground truth very well. So this is a comparison, but it doesn't mean the original pins without the NDK cannot get a good result. So we increase the hidden layers of the neural network size, and also we increase the bench size for the inputs. And again, at the same time, we need to adjust the weight by the hand tuning. And in that case, we can get a same level accuracy, but it will have more computational expense. And as we know, we don't like the out of the memory, and it is always happens when we have a larger bench size. So the NDK-based methodology can at least help to accelerate the training process, reduce the bench size, reduce computational domain. So that's one of the benefit of the NDK-based approaches. And then we also can compare the estimate state. So this is for the deflection. So the first is the ground truth. Again, I use finite and modeling to get the ground truth. And the up one is for the PI pins without the NDK. And this is the difference. So we can find a huge difference. And the low one is for the pins with NDK. So we have a relatively smaller difference. And this is L2 normal error. We can find for the NDK, it is reduced it significantly. And for the next slide is compared with the velocity. So again, we can find the NDK methodology can reduce the training error, reduce the errors of the stage. Okay. Thank you. So for previously slides, I just give very briefly introduction of the developed framework, and I try to give details about how I apply the pins to solve my own problem. So we developed a PI pins framework, which can be used to economic the structural discontinuities by dividing the entire domain into the subdomains. And for each subdomain, we will introduce an individual neural network. Through a parallelized and interconnected neural network, we can solve continuously structured systems with some discontinuities. And also we extend the framework by introduce NTK-based self-adaptive loss weighting function, which can help to overcome the discrepancy of the convergence rate between each loss components. So in that case, we have a more balanced training process. And we applied particular on one example to demonstrate it can be used to estimate the those structural parameters and also to predict the states, the full states, just based on the limited and noisy sensor data. And all this work are based on two publications. One is a public one, and another is under review. So that's about my work. And I talked a little bit about the ongoing work. And previously, I'm a PhD student. At the very first beginning, I focused using the finite and modeling and the common filter methodology to solve the structure identification problem. And inspired by the PI pins, the pin works, I found if we want to combine the pins, the machine learning into the physics, I guess the pin maybe is the only way and a very powerful way to do the identification, the inverse problem. So for the ongoing work, we try to introduce the damage with some mechanics to solve the creep damage or the cracking. And these three are the ongoing work. And for the future direction, we try to learn more besides the pin and also the deep ONet, which is also a very powerful tool to solving the inverse and the forward problem. And also I try to learn more about these methodologies and to solve the general structure mechanics, aerospace like structure identification problem. And in the long term, as we know, for civil structural engineering, some structure is very complex and large scale. So how to consider these issues, this problem can be a very huge challenge. So that's all my thought and inspired by the Penn work. And that's all about my presentation. And again, I'm very honored to be here to present my work. And thank you for your attention. I appreciate it.
Yeah. Thank you, Rui, for your great presentation. So now it's time to open the floor for questions. Are there any questions from the audience?
Hi, Rui. This is Somdatta from Brown. I wanted to ask you a couple of questions regarding the domain decomposition that you did. So if you could go back to the slide where you decomposed X and T.
For the numerical example or the general framework?
The general framework works. Yeah. So when you are decomposing when you are computing the loss at the interface, how many are you considering more collocation points over there, or is it the same uniform distribution of points that you have taken?
Yes, I use the total same 128, but for each iterations, I randomly select 128 points from this domain, and from the subdomain also the interface, and they have the same discrete lines. For example, if the square is 1 by 1, and the interface will have 100 points, or for example, have 1,000 points, and the governing equation will have 1,000 multiplied by 1,000. But for each iterations, we just select 120 points from these points.
Okay, and you specifically did not put any addition, apart from the slope and apart from the slope loss and the other one, I think it was the continuity loss. You did not have any other loss at the loading, at basically the support points, the interior support points.
Yes.
Okay. And another question that I had is, so you're solving the strong form. Have you thought about solving this in the weak form? Because probably that would be easier.
Are you talking about solving a weak form for the beam problem or the other problem?
For the beam problem.
Oh, yeah, that's a good question. It is also ongoing work because we treat the one advantage of the Penn work is the Penn can solve the PD in a strong form because it can avoid the truncation errors and also the quadrilateral errors, the numerical errors for the variational form. So that's one benefit. So that's why we start from the strong form. But just like your suggestion, if we can solve the weak form, it is a very good direction because it can be used to solve more complex, like the ODE functions has more degree of the freedom. But it is ongoing work, and I'm not quite sure it is an easier way compared to the strong form, in my opinion.
Yeah, because eventually you're finding out the energy. So you're coming to the variational form. So I think from weak to variational would be easy because both have have lower order derivatives rather than coming from strong to variational form. Probably it might be easier. Maybe it might be a good thing to try.
Yeah, thank you. Thank you for your suggestions. I will try to learn more from this. I'm not, right now, I don't have the good answer for your question.
Yeah.
Thank you.
Thank you. Great presentation. Thank you.
Thank you.
Thank you. Do we have any questions for the speaker? Yeah, I think there is no more question. Thank you for joining us today. Thank you everybody for joining us today. Have a great weekend. I think it's time to close the session. Bye everybody.
Thank you.
You're welcome.